Good day. In this video, I'm going to show us, or I'm going to teach us how to interface I2C device to AT51 microcontroller. But before we continue, let me briefly explain I2C and what it means. I2C is a communication protocol that helps you to connect your external peripherals to a microcontroller. An I2C communication protocol communicates using two bus communication protocol. That is, it have only two cable for connection. Apart from the power line, the VCC and the ground, it have only but two connection. That is SCL and SDL, serial data line and the serial clock line. And I2C peripheral or device comes in many forms. We have I2C memory EEPROM, we have I2C LCD display, we have I2C 7-segment display and other I2C devices. And it might interest you to know that these days the panels or embedded system that we have these days uses I2C communication protocol because of what? It reduces the number of input and output terminal that it will take from your microcontroller or microcomputer, like other communication protocol, parallel communication protocol that makes use of 8 communication line. We have SPI that makes use of 5 communication line. And once you are using any of this communication protocol or device that operates using that this communication protocol, you'll be rest assured that you'll be shorting of digital input and output ports. Depends on the microcontroller you are using. But with I2C device, you will only make use of 2 communication ports. And some embedded system that you have in the market these days comes with I2C interface. Like Arduino, it has a dedicated I2C communication pin, that is analog pin, analog 8, analog 4 and analog 5 is dedicated when you are making use of Arduino. When you are making use of node MCU, it equally have a dedicated I2C port. The same thing with Raspberry, it have a dedicated I2C port. But AT51 microcontroller that we are going to use on this video does not have any I2C port, any dedicated I2C port. You choose any of the input and output port that you like and you use it to communicate or to connect your I2C device. And in this video we are going to be focusing on interfacing I2C EEPROM to AT51 microcontroller. And the I2C we are going to be looking at, or our case study here is AT24C02. This AT24C02, let me open my protues so I can show you. This is the IC here. When we are talking about I2C, this is the I2C EEPROM that we are going to be looking at, 24C02. I2C device, it looks like a 5-5 timer, but it's not a 5-5 timer. It has total of 8 pins. But in our protues here, you will not see the VCC pin and the ground pin. They are internally connected because it's a software simulation. Then we have our P6, that is our SCK. We have our P5, that is our SDA. We have our P7, which is WP. We have our 1, 2, 3, which is A0, A1, A2. And this A0, A1, A2, we call it address, slave address. We use these particular pins to differentiate I2C device from the other one. Because I2C device, you can connect up to 4 or 5 I2C device on a particular I2C bus. You can choose to connect up to 4 or 5 I2C device in a particular bus. And this particular pin A0, A1, A2 helps you to select the slave address that you want to communicate to at a particular time. When interfacing I2C to a microcontroller, the I2C device is the slave, while the microcontroller is the master. Why we call the microcontroller the master is because the microcontroller is the one responsible for the communication initiation. Before I2C communicates, the microcontroller will initiate the communication by sending a start condition, and after the communication it will still send a stop condition, while the I2C device itself is the slave that receives information. It will not do anything until the microcontroller starts communication. If the microcontroller does not initiate communication, they will not communicate, and once microcontroller stop the communication, it will stop communicating. So that's why we call it slave, and the microcontroller is the master. So like I said before, you can connect up to 4 or 5 different I2C devices on the same I2C bus. So with the I2C address, you can be able to select the particular chip you are communicating at a particular time. Let me explain more. Okay, looking at the picture we have on the screen there, this is a full I2C address. It has a most significant bit, that is the first 4 bits, and the less significant bit. The most significant bit is a fixed sequence. It is a fixed sequence. It remains permanent. It doesn't change. The value there doesn't change. That is 1010. It doesn't change. But when we come down to less significant bits, the first bit, that is the first bit from the less significant bit, is the control bit. That bit, when you make it 0, it means that you want to send information to the I2C device. When you make it 1, it means that you want to read from the I2C device. Then the 3 other bits, that is A0, A1, A2, is the device address bit. Use it to select the bits, the device that you want to communicate at a particular time. How do you select it? On default, when you connect A0, A1, when you connect A0, A1, A2 to ground, that is this way, the way we have it here. When you connect this place to ground, automatically the first bit there, you have making it to become 0. And from the most significant bit, the last bit, that is the highest bit, bit 7 is 1, the second bit is 0, the third bit is 1. Looking up on this table we have here, when the first bit is 1, we select 8. When the second bit is 0, we don't select it because it is not high. Then the other bit is high, we select 2. Then the other bit is 0, we don't select it. So calculating 8 plus 4 will give us 10. And remember that 10 in hexadecimal is A. So we have A. We have A here on the most significant bits. Then coming to the less significant bits, when A0, A1, A2 is connected to the ground and the control bit is 0, what we have here automatically is what? 0. This becomes the slave address. A0 becomes the slave address. Let's take for instance that we have another I2C device that we connect on the same communication bus. On that one, A0 we make it 1. Then automatically we have changed the slave address. Looking up on this table now, when we have on the other the most significant bit, that is constant A, then coming to the less significant bit, that is this place, because we have made A0 1, the address has changed. What we are going to have here now, it will now become, making the control bit 0, what we are going to have here now as the slave address becomes what? A2. A2 becomes the address of the second device that is connected on the I2C bus. Then when we now want to write on the first one, remember this A0 happens to be the first device, A2 happens to